Okay, so now we're ready to talk about the variation of L'Hopital's rule that applies to infinity over infinity. Let me say the following. If the limit as x approaches a, now I'm stating it as approaching a letter A. There's actually variations on this that I'll mention in a moment. So we're just looking at it as approaching a single value of f of x is equal to either plus or minus infinity, and the limit as x approaches a of g of x is also either positive or negative infinity. Okay, and once again, we know that g prime of x is not 0 on an interval I when x is not equal to a. Okay, and so there's an assumption I haven't written down here that has to be true. So the same idea that had to be true here for the original version of L'Hopital's rule, they have to be differentiable. That still has to be true. So I'm not going to put that down, but that condition still has to be true. Otherwise, if they're not differentiable, then what we talk about really doesn't matter. Okay, so they have to be differentiable. And again, g prime is not 0 except maybe at a. Except maybe at a, then that's okay. So if this is the case, then we can say that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. Okay? So that is L'Hopital's rule. So again, if both top and bottom are approaching infinity, then as long as the derivative isn't like completely 0, so you can always then find an interval, then we evaluate it. So yeah, it could actually happen that you start with an infinity over infinity limit, and then when you do the derivatives, maybe you get a 0 over 0 limit. Okay. This limit process is also what I just said is true also for limit as x approaches positive or negative infinity, limit as x approaches a from below, and also limit as x approaches a from the right, from above. So if you had any of these limits and you replace the limit as x approaches a with any of those, then this result would also be true. Again, this result's known as L'Hopital's rule. So let's see a quick example of it. Limit as x approaches infinity of 7x squared plus 9x plus 4 over 12x squared minus 7x plus 6. Okay, so real quick, the only thing that's going to matter long is the leading term, the largest power. So the top's approaching infinity. As x goes to infinity, x squared is going to go to infinity. And so is the bottom. So this is an infinity over infinity limit. So we can invoke L'Hopital's rule and take the derivative, get limit as x approaches infinity of 14x plus 9 on the top over 24x minus 7 on the bottom, which is again another infinity over infinity limit. So we can invoke L'Hopital's rule a second time. Do the derivative of the top, which should be 14. Derivative of the bottom, which should be 24. 14 over 24 should be 7 over 12. Should be 7 over 12. Now, that works, and that shows you the L'Hopital's rule works. However, I want to point one thing out when you're dealing with algebraic fractions like this, where the top and bottom are just polynomials. Turns out there's actually a quicker way, and I actually teach this when I teach this limit in Calculus 1 without L'Hopital's rule. And that is that the only thing that matters in the top is what's happening to the largest power. So the top, I say this limit is the same as what's happening with 7x squared, what's happening with 12x squared. Right? Just looking only at the leading powers, because those are the only things that matter. Right? They're going to dominate what's happening, the x squared part. And so therefore I can rewrite this problem and say, well, this thing is equal to this. And then the x squareds would cancel out. And we would just get 7 over 12. So that's a quick little thing we can do. It's actually a little quicker than using L'Hopital's rule. Because the process we use, the long process that we used back when we did these limits, was to divide both top and bottom by the largest power of x. That was the long process, but that basically just can be shortened this way. And that works when you're dealing with a polynomial over a polynomial. If it's something else, then you got to deal with it that way. Okay, but polynomial over polynomial, you can actually shorthand it this way. Okay, so there we are. And you can see that the result does agree with our L'Hopital's rule either way. So this is just a little quicker way you can apply if you're dealing with just a polynomial over a polynomial. Just speeds it up a little bit quicker. Okay. But we'll see some other places where we can't do that, right? And we're going to have to use L'Hopital's rule.